Okay, let's get started. I realize I'm a few minutes late, but shouldn't matter too much. So welcome to week 7. Um, we only have one more week to go. It's so sad. What will you guys do on a Thursday afternoon from now on? Anyways, let's get started. So the first thing that I wanted to talk about was the glycolysis and gluconeogenesis. So one of the things that will come up is knowing the difference between the irreversible steps and then the differences between glycolysis and gluconeogenesis. For the most part, you're not going to have to memorize the pathway or anything, but knowing some key steps and understanding the irreversible steps and what's going on there is important. If you have specific questions, do please ask, but for the general, for I guess the sake of what I'm going to say is it's fairly simple in terms of, since you don't need to know the exact mechanism of the reaction, essentially all you're understanding is the concept that the irreversible steps need to have, or on their own will have a positive delta G, but when you couple them with ATP or other reactions that will drive the delta G negative, and that's what's going to cause it to be irreversible, is because it's going to take a second molecule. And for the example of like hexokinase, which I need to get a pen. For the example of hexokinase, right here, we're using ATP to phosphorylate the glucose molecule, and so you can't just reverse that and get the ATP back, because that's not how energy transfer works. There's not an enzyme that will transfer back the phosphate to an ATP, and so thus it's an irreversible step, because you have to use a whole other set of enzymes to even remove the phosphate in the first place. But again, that step in and of itself is also irreversible. So the kind of the main thing is to keep in mind is that those irreversible steps are the steps that are going to be used to regulate the process of glycolysis or gluconeogenesis, depending on the context that the cell is in. And I have some slides, or I have a slide that's coming up that will kind of better illustrate that. But again, just kind of look at this in terms of what's going on. You have the glycolysis irreversible steps. There are 3 main ones. There are 3 irreversible steps in glycolysis, and they are the phosphorylation of glucose, the phosphorylation of fructose 6-phosphate to fructose 1,6-phosphate. Just as a side note, keep in mind when we're talking about fructophosphatase kinase 1 versus 2, fructophosphokinase or FPK1 is going to produce fructose 1,6-bisphosphate, whereas FPK2, the enzyme that we'll get to later and that Aaron talked about in somewhat in chapter 12, but the I hate acronyms, by the way, but the FPK2 enzyme is not going to make 1,6-bisphosphate. It's going to make 2,6-bisphosphate, which is a different chemical because of the fact that it's got a phospho group on a different carbon. But again, we'll get to that in a little bit. But yeah, so the main point that I'm just kind of showing with these first couple slides is just what are the irreversible steps, and then what is the energy requirement in those steps. There is one thing I do want to point out. I didn't want to just take time to show the video, because it's not necessarily the most relevant for this talk, but it is a funny video about glycolysis that is hilarious, and it's an accurate video. So if you want to take some time and check that video out, please do. It's hilarious, and yeah, that's all I'll really describe about it. But back to the slide, when we're talking about the irreversible steps, we're really just talking about the steps that are going to be regulated very closely in order to make sure that we're not doing both glycolysis and gluconeogenesis at the same time, as well as the steps that are going to be requiring some kind of energy, or they're going to be positive delta Gs, and so we're not going to be able to go backwards once we've completed the reaction. So this slide kind of illustrates that point about what I'm talking about when I say some of the irreversible steps are great regulator steps. So the two steps that are being shown here are the second and third irreversible steps in glycolysis. So we're looking, for that third slide, we're looking at this reaction and then this reaction. So again, fructose 6-phosphate to fructose 1,6-bisphosphate, and then, as it points out several steps later, the regulation of phosphoenol pyruvate to pyruvate. And it should be fairly straightforward, but the red are inhibition molecules and the green are activation molecules, or helping to turn on the process. Several of these are not going to be important, like citrate, that's from the TCA cycle. Alanine, we're not looking at amino acid metabolism, but it is of note that there are multiple players when it comes to the regulation of these steps. And so when we talk about the irreversibility, or when we get into like molecules like fructose 2,6-bisphosphate here, we find that they help to regulate the process of either gluconeogenesis or glycolysis. And so it'll come up later, because I have the slides about the fructophosphokinase 2. But just to kind of talk about it for a second here, when we talk about those two different enzymes, the FPK1 versus FPK2, we're essentially talking about what product they're making. So FPK1 is going to make terrible K. It's going to make the fructose 1,6-bisphosphate, phosphorylating the fructose 6-phosphate. And so that is essentially, that is an intermediate within glycolysis. But you can also take this fructose 6-phosphate and shuttle it through to the enzyme FPK2, and that'll make the fructophosphokinase. And so in this case, to just kind of go over this example, the creation of the phosphorus, so you would presumably be in a state where you have glucose and you need energy, and so you're using glycolysis to produce that energy. And so you would have an accumulation of the 1,6-bisphosphate, and so you're going to have some of the substrate, the fructose 6-phosphate, going to the other enzyme, and so that's going to enhance the ability for glycolysis to function, because we're going to not inhibit, but we're going to activate. So that's why there's a plus sign on the glycolysis side. But that production of the 2,6-bisphosphate will also inhibit the production, or the pathway of gluconeogenesis, because the cell is in a state where it needs energy, and so it doesn't want to lose energy making glucose when it really just wants to burn that glucose in the first place. And then you can see kind of what Aaron was talking about the ATP and ADP and AMP inhibiting and activating. So, if you're in a low energy state with AMP, then you're going to want to make more ATP, versus if you're have a lot of energy like ATP, you're going to want to, you may need sugar in that case, as opposed to needing energy. And so in that case, you would be inhibiting glycolysis. There's no ATP on this side. It does help. Like if the low ATP levels would, or high ATP levels would kind of be a sensor, but the bigger sensor would be the intermediate molecules in glycolysis in the TCA cycle. That is, again, the TCA cycle is not going to be on the test, or I don't even think he covers the topic. But the point would be that there are other molecules that are indications that you have an increased amount of ATP, because you're getting an accumulation of intermediate steps. And then I really wanted to kind of just go back over the kind of the NAD, NADH pools and like why we want to maintain them. So if you don't have the ability to if you have, say you don't have this malate aspartate shuttle, and all you can do is make NAD from the oxidation of glucose to pyruvate, well, then you would run into a situation where you have no more NAD plus to oxidize, or sorry, to reduce into NADH. And in that case, your system would essentially stop. It would be like losing all sugar for the brain. You just wouldn't be able to oxidize or reduce anything, and so your cells would eventually die because of that lack of ability to maintain an oxidation reduction process. And so with the malate aspartate shuttle, this is an example of I don't know what else to use, but like conserved shuttle. And that's not like a scientific term, but I'm using the word conserved to suggest that we're maintaining our NADH and NAD energy equivalent. So the cytosolic NADH is not going to be transferred to the mitochondria, but the energy equivalence, the high energy electron that is reducing NAD to NADH, is going to be transferred using malate into oxaloacetate, and then you have to convert that back to alpha-ketoglutarate, so you can use an anti-porter system to pump malate and alpha-ketoglutarate at different directions, and then you have to maintain your glutamate aspartate so that you can convert oxaloacetate to alpha-ketoglutarate or alpha-ketoglutarate to oxaloacetate. And so one of the things that should be noted is that this malate to oxaloacetate to malate is part of the citric acid cycle, or the TCA cycle, or the Krebs cycle, all in the same cycle, as well as the intermediate oxaloacetate is a step in the TCA cycle. So you can see how even when we're not talking about another cycle, it's still interrelated with the cycles that we are talking about. And so that huge chart he showed during one of the lectures of metabolism, the main point to draw out of that is that metabolism is not an isolated system. It's an interconnected, interacting system that you can take one intermediate from one place and it may be a critical or a subset of one pathway, but it's just a random output or just a used system. So like malate or oxaloacetate to malate and then back again, when you're doing the Krebs cycle, that's important so that you can get back to the starting molecule because it's a cycle. But in this case, all we care about is that we can utilize the oxidation reduction potential of NADH to NAD to convert oxaloacetate to malate so that we can transfer that energy into a place where we can actually use it. Because one of the things that I said last week that should be restated this week is that when we think about energy molecules, we have ATP, which is kind of universally used throughout the cell, and kinases use it to phosphorylate proteins. You couple reactions with the breakdown of ATP in order to facilitate getting a negative delta G. But you can't do that with NADH or FADH2. You can't just readily break them down as by some random protein and get the energy out. It's more like gold or silver that you have to go to an exchange place to get cash that then you can go use in the economy. And so ATP is more like cash, where NADH and FADH2 are more like the precious metals that you need to exchange for cash. And so this allows you to maintain, you could think of it as a equivalent exchange rate. So you put in one gold bar and you get in one gold bar out. Whereas the glycerol phosphate shuttle is an example of a non-conserved shuttle. And then again, using that term is incorrect because I'm not using it in a scientific way. I'm just trying to get the idea across that for this example, we start with an NADH and we end up with an FADH2, which when at the end of the lecture, I'll kind of explain why that's significant when it comes to the electron transport chain. But the bigger point here is that we're not maintaining that the energy equivalent. And so this is
we're actually losing some energy by transferring the NAD from the cytosol into the mitochondria. Skeletal muscle, the glycerol phosphate shuttle is prominent in, and then the malate aspartate shuttle is prominent in the liver. But these are just two examples of how you can maintain the NADH-NAD pool within the cytosol, and so you're not running out of those reduction potential molecules. The third way that you can maintain that pool and replenish your NAD versus NADH pool within the cytosol is lactate fermentation, at least for humans. It would be ridiculous if we could do what yeast can do and ferment into alcohol, but it's probably for the best that we can't. And so this slide is just kind of illustrating that, or how that works. And so, you start with glucose, and then you go through glycolysis, producing your NADH reduction, your reduced NAD to your NADH. But you want to get back that NAD8 or NAD plus so that you can keep oxidizing, words are hard, so that you can keep reducing the NAD plus to NADH, so that you can maintain this getting ATP out of glycolysis. Because if you're doing fermentation, you're doing anaerobic respiration, so no oxygen is involved, and so you're not going to the mitochondria. And because you're not going to the mitochondria, you still need to maintain a level of ADP in case you need to run away from a bear or something. And so the lactate fermentation is going to facilitate you maintaining an ATP level, an energy level, so that you can, escape if necessary. But the problem is that we can't break down lactic acid very well. So it accumulates, and then it'll get transferred, it'll accumulate in the muscles and cause them to burn. So, like if you've ever heard of lactic acid burn in your muscles, or someone's working out and they're like, oh, my muscles are really burning. That's lactic acid in their muscles, in their muscle tissue. And, as acidic things burn. You spill acid on yourself, it's going to burn. So this isn't going to burn you like that, but it is going to give you a burning sensation. And then a lot of times the lactic acid will then start to accumulate in the stomach. So if you ever get a sour stomach from running and exercising a lot, this is essentially what's going on. You're not going through aerobic respiration. You're kind of stuck in anaerobic respiration, and your body will go through and convert into aerobic respiration, but so it's going to take a while. And so lactic acid fermentation is kind of a stopgap procedure that your body is going to use to maintain your ATP levels. Excuse me. And so because of that, you need to maintain your oxidation reduction potential. So and that's why you need to ferment pyruvate into lactate, so that you can maintain your NAD versus NADH pool. And just to kind of show you how other organisms do it. So I mentioned that we can't convert pyruvate to alcohol, but yeast can. So whenever you're brewing beer or anything, this is what's happening. They're going through anaerobic respiration, producing ethanol, whereas we produce lactic acid. So, different organisms employ different biochemical pathways in order to facilitate the same idea. The whole point is to maintain your NADH and NAD ratios. So, yeast figured out a way to make something that we like, whereas we make something that hurts us a little bit. Or I guess not hurt, but makes us uncomfortable when we exercise, when we're out of shape. So this slide is kind of just a transition slide into what I was talking about in terms of I forgot to put a 1 there. There we go. Into the, did I write that wrong? Oh, I've been saying the acronym wrong. That makes sense. So fructophosphokinase, or phosphofructokinase, sorry. Like I said, I'm terrible with acronyms. So this is the enzyme within glycolysis that is going to convert fructose 6-phosphate to fructose 1,6-bisphosphate. And that's what its job is. But it is regulated by this fructose 2,6-bisphosphate. Both of the enzymes are. And so this is just in trying to help get you guys to understand and make it kind of more clear that even though they have similar acronyms, they're doing different things. So one is producing a molecule that's not used in glycolysis other than a allosteric inhibitor, whereas PFK1 is producing an intermediate step within glycolysis itself. So if this slide looks familiar, it's because I stole it from his lecture. And so good on you for noticing that. But the point that I'm using is, or the point that I'm making is that you have two signal molecules that are going to signal for different things. But you got to remember that these signal, the glucagon signal and the insulin signal, are not going to be produced at the same time. They are going to be regulated in a way that is reflective of the needs of the body and the needs of the cell. So if you need glucose, then you're going to release a glucagon receptor, or you're going to release the molecule that will bind to the glucagon receptor. And if you need to intake glucose so that you can utilize it for energy, then you're going to produce insulin, and then that's going to bind to the insulin receptor. Excuse me. And so all this really is saying is that when we have high blood glucose, we're going to take some of that glucose that has been converted to glucose 6-phosphate and then isomerized to fructose 6-phosphate. Excuse me. And we're going to use that to either enhance and then repress our opposite. So we're going to enhance the activity that we're wanting. So we're in this case, if we're going with the insulin, then we are enhancing the activity of our phosphofructokinase 1. We're going to positively affect the conversion of fructose 6-phosphate to fructose 1,6-bisphosphate. And so that we're going to encourage the uptake of glucose. We're going to get that energy out, and the cell is going to be happy. Whereas if the cell has a lot of energy and say it doesn't need all the energy that is around, then and say like the brain, or I guess the best way to put it is you have energy, but you need more energy. And so when you have low blood glucose, so the brain, as you know, can't store glucose, and so when it's starved for glucose and it needs more, and you're not taking any in, for maybe you're on a low carb diet, or you're just trying to watch your weight, or maybe you're trying to bulk up for some competition or something, but you're not taking a lot of carbs or sugars. And so in this case, you would have low blood glucose, and then you would have a receptor that's sending to glucagon receptor that then facilitates the activation of the FBPase2, which is inhibited by the activity of the PFK2 enzyme. And so they're counteracting enzymes. And then if you activated the FBPase2, then you would produce glucose as opposed to breaking down glucose. And so how that all goes down, and I realize this picture is kind of granular, but the main point is here in that. Sorry, I can't see my screen. Too many things. The main point is that when you are when you have like high blood sugar and insulin is signaling, then you're going to, if I get this right, yeah, okay, there we go. Is this flipped?
Okay, sorry. I just had to orient myself. So when you have the dephosphorylation, I'll write this in, the FK2 portion of the enzyme is active, and so it's going to produce the or the fructose 2,6-bisphosphate. And as we've learned from the previous chapters, the reason that it's active in one state versus the other is that since these proteins are connected, any change to one is going to have some change to the other side. And so when we add a phosphoryl group or a phosphate group, that is going to cause a change in the conformation of the protein. When, as we know, a change in conformation leads to a change in function. And so when we remove the phosphate, it's going to change the shape of the enzyme such that it inactivates the FPase2 and activates the PFKA2. Whereas when we phosphorylate PFK2, that's going to inactivate it because it's going to change the conformation of the enzyme in such a way that it inactivates PFK2 and then causes an activation in FBPase2. And so again, all of this is trying to show you is that modifications change the function of the enzyme, or change in shape, change in function, and the addition of in this case, a post-translational modification will induce a change in shape. And so that we can use that post-translational modification in order to regulate this enzyme and then regulate whether or not we need to produce sugars because we're in low blood sugar, or produce high sugar, or break down the sugar because we're in high blood sugar. And again, if you all have any questions or anything, even about the test that's about to end, or the upcoming test, just please write down the question and stop me and we'll go over them. So again, I just put this slide in again just to kind of reemphasize that what fructose 2,6-bisphosphate is doing is just acting as an allosteric activator and allosteric inhibitor for this step within glycolysis. So we're just using this step, or we're using F26BP in order to regulate whether or not we are converting fructose 6-phosphate to fructose 1,6-bisphosphate. Because as we know, this requires energy. And if the cell doesn't want to use that energy to break down glucose because maybe it doesn't need to anymore, or like I said earlier, you want to, so you're going to want to enhance it. That's going to be a way that we can regulate this step. And so because it's irreversible, we have a highly regulated system because we can just turn off the enzyme and then the enzyme can't convert back into the product to make more product. So once we shut off the enzyme, we won't get any more product out of that enzyme until we activate it again. And so the last little bit that I have planned for our little talk is this slide has relevance in the idea that glycolysis and the electron transport chain are connected through the citric acid cycle. But the citric acid cycle is not on the test. It's not, he doesn't cover it in the lecture, so it's not relevant for memorization or anything. But it is relevant for understanding that there are intermediates within the citric acid cycle that will affect, that we can use to, in gluconeogenesis, and then, we'll get high energy molecules like NADH and FADH2 from citric acid cycle, and then we'll all go to the electron transport chain. And that's why oxidative phosphorylation is much more efficient in getting more energy out of one glucose molecule than the equivalent amount of energy you'd get from fermentation alone. And one other thing that I think that this picture does just a beautiful job of is one of the concepts that you will need to understand is this idea of oxidative phosphorylation. And that may sound kind of confusing when the context of like what's oxidative phosphorylation versus something else. So why we distinguish oxidative phosphorylation from this substrate level phosphorylation is that we're using the high energy molecules NADH and FADH2 to oxidize. We're using the oxidation reduction potential of the NADH and FADH2 to make ATP, and so that's why it's oxidative phosphorylation versus substrate level phosphorylation, where you're using just another high energy molecule in order to add a phosphate onto ADP. The oxidative phosphorylation is going to use the oxidation reduction of NADH and FADH2 in order to facilitate the creation of ATP. And so I do know that term is on the review for the last test in terms of concepts that he wants you to know. And so we'll go over them next week, but I just thought I'd bring it up. Sorry. I just thought I'd bring that up this week and kind of get your appetites wet a little bit. So the main concept when it comes to the electron transport chain is the idea that we're using NADH and FADH2 and we're going to oxidize them back to their NAD and FADH form, NAD plus and FADE forms. And then we're going to use that energy that we're getting out of them to pump electrons across the membrane into the interstitial space so that then we can use that electron potential gradient to produce our ATP. So it's not a direct, we're using the NADH and FADH2 to make ATP. We're using them to create an energy potential that then allows us to extract the energy, use the energy potential to kind of extract the energy and make ATP so that we can store and use that later on. Things to note is that the reason NADH is going to get you more ATP equivalents than FADH2 is because of the fact of what complexes pump hydrogens. So when we talk about the electron transport chain, you talk about complex 1, 2, 3, 4, and then ATPase is usually called complex 5. But the point that I'm making is that you're only pumping hydrogens in complex 1, 3, and 4, but FADH2 only uses, in terms of pumping complexes, 3 and 4, whereas NADH goes through complex 1, which also pumps. And so you're getting more hydrogens pumped across per NADH than FADH2 because of the fact that FADH2 uses complex 2 in order to get into the electron transport chain, and complex 2 doesn't pump any protons. And because it doesn't pump any protons, you're not getting the benefit of going through the complex 1 with the NADH. And that's why, if we go back up to the glycerol phosphate shuttle, that's why in this shuttle, you're not getting the equivalent of energy back out. You're losing some energy when you transfer the NADH and the cytosol into the mitochondria. It's just the way life decided to make the pathways in the cells. But that's just this kind of the way it is. This picture kind of gives you a better I think it gives you a better understanding in the sense that if you're talking about NADH, you're not going to care about complex 2 because it doesn't ever interact with complex 2. It goes through the complex 1. The electrons get transferred down to an energy state that quinone, the Q, can bind to. Then quinone transfers the energy to complex 3, where it steps down again and goes to cytochrome C. And then cytochrome C passes the electrons onto complex 4. And complex 4 is where the electrons actually get added to get added to oxygen to create water. And so this complex 4 is actually where the electrons are going to stop in both cases. The difference for FADH2 is that, so one of the things that
is not talked about in the class is that, the citric acid cycle is going to play a role in making a lot of the high energy molecules in ADH and the FADH2. But one of the steps within the citric acid cycle is this succinate to fumarate. And that is essentially what complex 2 is. It's this conversion of succinate to fumarate, and then that produces an FADH2 molecule. And so essentially the reason you're not going to use complex 1 is because you're already in complex 2 when you make the FADH2. And so it just transfers the electrons to quinone, and then that goes down the line into complex 4. And then this picture kind of gives you, shows you a visual of kind of how the electrons are kind of stepping down, or kind of, transferring from the different complexes to the final complex 5. It's nothing you have to memorize. I just thought it was a fun picture to kind of look at and kind of give you a visual understanding of what is going on when we talk about the transfer of electron down the electron transport chain to the complex 4 and the formation of water from diatomic oxygen. Oh, and I should just keep in mind that the citric acid cycle and the electron transport chain are all going to be in the mitochondria. When we talk about it, this would be this. I don't know what color this is exactly, but this salmon color is the matrix, and then this is the inner space. Right. So just keep that in mind. It just kind of helps you make sure that you you know where you are in the cell, and so you're not going to say, "Oh, we're in the cytosol," and then someone's going to, "What are you talking about?" So complex 5 is fascinating. It's one of my favorite proteins, but it is a fascinating molecule nonetheless. So I will go further into depth for the next recitation in terms of the ATP synthase and the inhibitors and everything that we can talk about in terms of this. Excuse me. But what I really just wanted to go over this week is kind of just introduce you to what is complex 5, what is ATP synthase, because it is a fairly complicated molecule. I mean, essentially, it is a motor. Like you think of an engine, or like a electric engine or something like that. That's essentially what we're talking about. We're talking about we're putting in hydrogens on one side, getting them out the other, and then that rotation, that energy from the hydrogen is going to cause the whole system to rotate. And you have this arm here that is holding this spindle to this, ratchet, if you will. And so that's kind of how it's all being held together and how it's all working together. This picture is just a crystal structure of ATP synthase. I just think that looks cool. And you can see all the alpha helices, and then, how the what's typically called the C domain is full of it's just alpha helices, and it's spanning the membrane. And, you can just kind of see all of the things that we've seen in terms of this is a whole quaternary structure. There's a tertiary structure. These are this is I think it's a homohexamer, it's not. It's a heterodimer hexamer. So it's six subunits of A alpha and beta, and those alpha and betas are together. And so this is a heterodimer, and then this whole thing is a hexamer or something like that. But the point being is that it's a very complicated system, but fairly straightforward once you kind of get it under your belt. Just minimize chat, and I didn't mean to, so sorry. Just give me a sec. All right. So what is driving this whole system is the input of the hydrogens into the C ring that we pump through from complex 1, 3, and 4. And so they aren't full channels. So that's kind of one of the bigger concepts to make sure that you understand when you're understanding this, how this ATP synthase works. And I might be going into a little bit more detail, but I'm just kind of nerding out, so bear with me. The point is that if you had a full channel, if you were talking about you had a full channel through this membrane, and you had hydrogen, and the hydrogen could just go through, and how are you going to capture any of that energy, right? And so what the system does is it has half channels, and so it forces the hydrogen through the membrane, and so through a region that it doesn't like. So you're essentially getting potential energy and then converting it to kinetic energy, if you want to think about it like that. So in this instance, I think it's upside down. But the point being is that whichever way you want to look at it, say this is the where we're going to produce ATP, so we're going this way. So the hydrogen comes into the channel, fits into a slot within the C, in one of the C subunits. Then that rotates, but it doesn't rotate towards the other hole. It rotates the other direction, so kind of the further direction around. And so you can get multiple hydrogens in this ring, and so that you can just constantly cause the motor domain to rotate. And I can't get rid of chat enough. There we go. And so this rotation is then going to come around, and then you're going to rotate to the second channel, in which you're going to then lose the hydrogen. And I believe that this step is just showing kind of what would happen if you kind of showed multiple. This is kind of showing, like, again, a final step of this rotation, as opposed to going back through this whole system. Sorry, I went backwards. My bad. So you're going to get close. Another one's going to come in. You'll lose your first hydrogen, and then this will swing back around, bind, and then continue on. Sorry, see, everybody makes mistakes. Just got to admit them. And so the point is that you're using the hydrogens that you pumped across the membrane in order to help facilitate this rotation of the C subunit that then causes the rotation within the motor domain. One thing to note when we're talking about the ATPase, this C12 that I'm trying to circle, it literally just means that there's 12 C cylinders going around. It could be C10, it could be C8, it could be C16, just depending on the species, it will change. And so essentially, it just changes the number of rotations that the C subunit takes before it completes one full rotation. And one full rotation will get you 3 ATP, as we'll see in this last slide. So this is just showing you the kind of the biochemical process of making ATP using ATP synthase. So you have 3 alpha subunits, which are the open areas that you see in this diagram. And so you have, so we'll follow the NAD or ATP, ADP, and phosphate. So you have it binding to the open spot. So that's an O, it's open. And then it rotates. So the L spot rotates to where our ADP plus PI is. I think that's the loose binding. I think L, if I remember correctly, L just means loose. So it's a loose binding. And then that's going to essentially be the transition step that you see no reaction in terms of in terms of the molecule we're tracking. If you were tracking the other one, just to kind of note, I'll put them in a different color. That'll make more sense. So if you were watching this guy, there was no reaction from the tight binding, which is the T, but there is conversion to ATP from this before you rotate to this open step. So this kind of transition is once you bind the tight, and you get tight binding, you're going to convert the ADP and PI to ATP. So tracking our favorite one, we're in the loose state, or in the loose binding, and then we'll go to tight binding, which is then going to get converted to ATP, and then again we'll have another rotation and go to the open form, and then we'll have the loss of our ATP from the binding site, and so we've made energy from a electron transporter like ADP or like NADH or FADH2. Yeah, that's kind of all I had for today. If you have questions, please ask, and I'll stay around for you guys' questions. I know that the other the test 3 is ending. I think it's Sunday, and then the final should be up on Sunday as well. So that's really all I have for today. So if you have questions, please ask. Yes. The next session, or the session, will be same time, same place, and that will be the last time we meet for recitation. It'll be the 8th recitation and the final one. The major topic for that the major concept that I'm supposed to go over is the inhibition and regulation of ATP synthase. So I thought I would introduce the concept this week and get more into it next week. So yeah, if you're free next week, please come enjoy the last time we'll have together. So when you say delta G is less than 0 for an irreversible step, yes, that's true, but when we're talking about the coupled reaction. So to go back up to the top, I don't have in his slides in his lectures he talks about what the actual delta G is for just the reaction without like coupling it, and they are positive. But the point is that it is a favorable reaction, but because we're using energy or like the phosphatase, you don't see the usage of energy in this step, but it is requiring some energy, and then it's irreversible because you're not going to use ATP to convert back. So it's probably a bad example. The better example would be stupid thing. The better example would be down here, where you're actually using ATP or GTP to convert. And so these reactions are not going to be favorable unless you use that energy equivalent to make them favorable. And that's, again, one of the reasons why it's an irreversible step, is because you're committing to using that energy to get back out the step. Or in this case, you're getting energy out. So you're going from a high energy molecule to a low energy molecule, and you would need to produce energy. So it's, I guess, the better answer to the question of, is delta G always less than 0 for irreversible steps? Yes, in the biological sense that the reaction is going to proceed but no for an individual reaction, and it really depends on what the substrates are for that reaction. Like I know just off the top of my head that the
it's positive. Glucose, the phosphorylation of glucose to glucose 6-phosphate without ATP is a positive delta G. But when you add the breakdown of ATP into the equation, then it becomes favorable. So that would be an example of where the reaction itself is not spontaneous, but when you couple it with the breakdown of ATP, it becomes spontaneous. And again, I think it's the latter section. I think it's the latter sections of 11. No. Yeah, I think it's either the latter of 11 or the beginning of 12. But he does go over this in pretty good depth. So if you're having any questions in regards to what the exact numbers are, I would just refer to the lecture videos, because he does a beautiful job of that. What is the... So I'm looking up the practice test questions because I don't know them off the top of my head. Oh no, it's perfectly fine. I just have to take a second to look them up. And that was that practice test 3, I assume? Good. Oops. Oh, all right, there we go. There we go. It's opening finally. All right. Yes. So yeah. So when it's talking about, so I just kind of go over the specific one that is the... Sorry. So what I was saying was that the irreversible step needs to be much less than 0 because it's irreversible. A reversible step is closer to 0 or equal to 0 because then, depending on the amount of substrate or product, you can drive the reaction forwards or backwards. A great example is the glyceraldehyde 3-phosphate and the dihydroxyacetone phosphate. So the reaction itself drives towards or dihydroxyacetone phosphate. Like when you can use, I forget the enzyme, but I think it's isomerase or enolase. Either way, it should be up here. Aldolase. Sorry, when you use aldolase and you convert fructose 1,6-bisphosphate to either dihydroxyacetone phosphate or glyceraldehyde 3-phosphate, you end up making the reaction in itself is going to want to make more dihydroxyacetone phosphate. But because glyceraldehyde 3-phosphate is a substrate for a subsequent reaction, you will deplete the pool of glyceraldehyde 3-phosphate, driving this reaction forward. And so because the delta G is close to 0, you can use that mass action to drive the reaction in the direction you want. But if you had an accumulation of glyceraldehyde 3-phosphate, then the reaction could go backwards and produce dihydroxyacetone phosphate. And so when we're talking about delta G being much, much less than 0, the reason that it's true for irreversible steps, or it has to be for an irreversible step, is because the step is not going to be converted backwards. And so the reason it's such a high negative delta G is because that you're using so much energy to get it down to cause the reaction to go forward that it's so much less than 0 that it won't go backwards. And so a reversible step would not be true for this statement because of the fact that it needs to be close to 0 so that you can go forward or backwards. I hope that makes sense. So, and again, sorry for the muting. I don't even know how I did that. It's always good when you get the more understanding we can get, and the more comprehension we can get, then the better everybody's time will be. And then it makes the test less stressful, which I can appreciate. Don't like tests. But if there are no more questions, and it is 6 o'clock, so I'm going to get off. But if you do have a question, type it in the chat right now and I'll answer it. If you come up with a question after we end, please feel free to email me and I will respond as quickly as I can. But everybody have a great night, unless there's another question. Nope. All right. I'm going to end it. Boop. Doop.